All right, welcome to SF 430, Materials and Manufacturing Processes. This is lecture 1, Course Overview and Materials Fundamentals. My name is Hao Zhang. I'm assistant professor at School of Integrated Sciences at James Madison University. First, I'll give a little bit of introduction about the course overview. And so we have this manufacturing curriculum in SF, and you have already been through 2 years of manufacturing knowledge. So in the second year, you had a 211. Mostly you're talking about it was talking about manufacturing fundamentals, for example, how products are made, supply chain, and a little bit about continuous improvement and also different production systems. And in the third year, you have taken 330 and 331 as well as 303. So for 330, mainly was talking about production planning and control, and 331 it has manufacturing automation, human factors, as well as a little bit about cyber physical systems. And also there's a hands-on experience lab course that is manufacturing automation. So this is what you had taken in the past. Well, when you concentrate in production system or industrial manufacturing systems, and there are also several courses that will help you further understand manufacturing process and systems. And I'll just go through some of those. So material manufacturing processes, this is the 430. So in this course, then I want to talk about different materials, engineering material, and how they are used in different manufacturing applications, as well as different manufacturing processes. Also in 430, we'll have a lab related to computer-aided design and manufacturing. There you will learn 3D design, product design, engineering drawings, as well as GD&T, and also computer-aided manufacturing. And there's another course, it's called 431. In 430, mainly what I talk about is a traditional manufacturing process. For example, different solidification like casting, injection molding, or cutting or machining, those kind of processes. While in 431, we're focusing on more advanced or novel manufacturing processes. For example, additive manufacturing, 3D printing, right? Macro manufacturing, macro machining, or laser technology, or nano manufacturing, and also digital manufacturing systems, as well as sustainability of manufacturing. So these are the more advanced technologies in manufacturing. And so this is the 430 and 431. Also, we have 433 and the 435. So the 433 and 435 deals with another major part of manufacturing, that is the management part, continuous improvement, supply chain, and Lean and Six Sigma. Mostly without JIT, different lean technologies like Kanban, with flow, push systems, and also some other technologies related to continuous improvement. And other than that, we also have a couple of other courses. For example, this is the 437 related to technological innovation and sustainable design. Then we'll talk about different policies, as well as different technologies related to sustainable design. And one more course is manufacturing informatics. So here, mainly it's about how to use data analysis to deal with manufacturing problems, including design experiment, different measurement, system analysis, quality and process improvement, reliability, and also big data. So that's these are all the different concentration courses. And so in 430, this course is this part, right? So this is what we're gonna talk about in this semester with 430. So after I give you this introduction about a manufacturing curriculum and look at where 430 is at, now you should have a better idea of what we will learn in this whole manufacturing curriculum with this course. All right. Next, a little bit about the course objective and topics. So the purpose of the class is to introduce you the chemical and physical properties of materials, metal, ceramics, glass, polymers, composites, and also some other sustainable materials, and also manufacturing processes, right? Solidification processes, surface finishing, forming, joining, and machining, those kind of processes, and also automated computer-aided design and the product design. And here are all the topics related to it, including material properties, product attributes, engineering materials and their applications, solidification process like casting and injection molding, process of metals and ceramics, so how the metals, metal sheets and metal forms are made, and also metal forming and sheet metal working. Metal removing processes are mainly about machining, cutting, and turning, and drilling, those kind of processes. And property enhancing and surface finishing processing operations related to how do you deal with the surface of produced products or parts, as well as how do you increase the property or enhancing the property of the materials. And lastly, they're going to talk about the joining, for example, the welding process, and also mechanical assembly, and what are the different ways of assembly in products. There is a textbook for this course, although you are not required to buy it, but because you are concentrating in this in manufacturing, so I will highly recommend you to have this book because it will help you not only in this course but also in your future career if you are in a manufacturing company or career. It's a very very useful and also very popular book in almost all engineering schools with manufacturing curriculum in U.S. And so this book is more about materials and process and systems. So it talk about all different kind of manufacturing processes. In the future, if you need some background knowledge or know a little bit more about a certain process in your work, you can always come back to this textbook. So I'll say this is the textbook it should be on your bookshelf if you're a manufacturing engineer or manufacturing manager. All right, next, talk a little bit about how the grades work. There is only one exam, that is final exam in the finals week. And also assignment will be 25 points. In this course, we also have a quiz, not one quiz, but have quizzes. So it also composes of 15 points. And another major part of this course is a lab. So for this course, in each week we have two classes. So one class will be lecture, and the other class will be the lab. And bonus points, I'll give bonus points, and it will be 5 bonus points. They will be randomly assigned, in some assignments. It might be in the final exam. It might be in the middle of the semester, or maybe in some of the lectures. And so for the course letter grade, as you know, if you read the syllabus, that I do not use percentage, I do not curve, I only use absolute points you gained at the end of the semester. And the bonus points are the 5 points that added up on your points that you gain from all the other assignments at home and exams. So totally you have 105. If your points are marked off like 20 points, then you will get 85, right? So 85, that will be you will get a B for the letter grade. So this is how to calculate your final grade and letter grade at the end of the semester. All right. In terms of how to get an A, if you want one, so for this course, there really is not a lot of maths, so not a lot of calculations, but there are some. More importantly, is it requires you to understand the logic. Why is it, right? Why is it, and also remember the some of the terms and also the materials, right? The content. So that's why I give quizzes, I give homeworks just to try to enhance your memory about those. For example, if you want to know different material, different polymers, there are many different kind of polymers, right? And it's not good that you only remember it in this course, and then after 1 year you forgot about it, and so that's not the purpose. So my goal is to help you understand the underlying logic, so you can have a long-term memory about what they are and how they are used and their properties, as well as the manufacturing processes. And the textbook, so most of the material from this course is from that textbook. So I highly recommend you to purchase this book if you haven't yet, and also read through the chapters, before the lecture. And for the homework, I will give homework almost after. Sometimes it will be 2 lectures. Sometimes it will be after 1 lecture, and also the quizzes. Quizzes will be after each lecture. And I'll post it, and you can finish that, and submit it. And for the labs, I will talk a little bit more about labs during the lab lecture, in the first lab lecture, and then I'm gonna go through more details about that. And the final exam. So one material will be covered in the final exam. Mostly it's about a quiz and also assignments, as well as what you did in the lab. So after each of the lecture, I will summarize some of the takeaways, so you know what is important in the lecture. All right. So the course schedule is scheduled with 13 weeks. Of course, there's there's some Thanksgiving or some other holidays, but for the materials, there are 13 weeks of course materials, and I think we have 17 weeks, including the finals week and that week. But the course material, we have 13 weeks. So the first part will be the material properties and also engineering materials. So because in order to understand how the materials are used in manufacturing process, and also how the manufacturing processes you can produce high quality of the product, you have to understand the fundamentals of materials and why materials behave that way. So that's why the first part will be the materials, and the second part will be many different traditional manufacturing processes, right? The solidification processes, materials removing processes, right? And processing metals, ceramics, forming, property enhancing, as well as joining and assembly processes. For the lab, you can have a snapshot of what is covered in the lab. So the first few weeks will be design, product design, and also CAD drawing, including one materials testing lab. It's a material tensile and hardness test. And then we have an injection molding lab to learn how to process polymers and use injection molding to make different shapes of polymers. and Turning Lab how to use a lathe machine, and the CAM how to design manufacturing processes in the computer-aided software, and also we will have several weeks of machining operations in a production system lab. And for in our lab sections, we are making an actual product, which is a JMU clock. So you need to design the clock with computer-aided drawing software, and then make each of the parts by yourself. So lastly is a laser engraving. So you can engrave some of the words, the text on the acrylic face, of the clock. All right. Now let's formally start our lecture with nature of materials. This is a little bit outline about the materials. We're going to talk a little bit about atom structures and elements, different bondings between atoms and molecules, and also different structures, crystalline structures and non-crystalline structures, and also what other engineering materials are commonly used in manufacturing. First, atomic structure. You already learned, chemistry and physics. You should be pretty familiar with the structure of atom. So it's the nucleus is composed of a proton and a neutron, and outside of the nucleus there are electrons. So a lot of times, actually, when forming the material structures, electrons actually play a big role in forming different structures of materials. And so this is a look. This is a camera look of what it looked like as a atom. You can see to the outside. So these are the movements of electrons. It does not mean that it have electron all over. It's just because it moves really fast. That's why it shows that it's a circle. Periodic table of elements. So something you just need to remember is the maximum number of electrons in an orbit is 2 times n squared, right? So remember, this is the maximum number of electrons in an orbit. It's not how many electrons outside in an orbit, right? For example, sometimes in outside orbits, it can be 1 electron, it can be 2 electrons, or it can be the maximum electrons to be at a stable state. So yeah, right. So if the outside orbit or the orbit has reached its maximum number of electrons, means it's more stable, right? If it is not, right, it's not stable. All right, now let's look at a simple model of atomic structure for several atoms. So the first one is hydrogen. You can see hydrogen, there's only 1 electron outside, and also some other elements. And something you need to notice is sodium. So for the sodium, you can see there's only one electron, at the end, at the outside orbit. So which means it can easily lose its electron. And this is how the materials are actually gonna form different bondings by losing and attracting or accepting electrons from another atom. There are different bondings, 2 different categories of bondings. So one is the primary bonds. Primary bonds mainly deals with how the molecules are formed, right? And the secondary bonds are attraction between molecules, right? So primary bonds are usually much stronger than secondary bonds. For the primary bonds, there are also several types of bondings. The first one is ionic bonding. So ionic bonding means the atoms of one element give up their outer electron, which are in turn attracted to atoms of some other element to increase electron count in the outermost shell. So basically, it's if one atom that the outside the outer orbit in the outer orbit the electrons not a lot, right, like only one or two, it can easily lose its electron and then be attracted to another atom. So then both atoms gonna achieve its stable state for the outermost shell. So in this case, we call it ionic bonding. So one gave up and one receive. So a very typical material that is sodium chloride. You can see sodium actually loses one electron to chloride, and the chloride receives the one electron, and both atoms can achieve its stable state of the outer orbit. And for covalent bondings, electrons are shared instead of give up. So shared means both atoms actually uses those electrons as the outside or outermost shells to achieve a stable state. And the methane is one example, right? So carbon has 4 electrons outside, 1, 2, 3, 4, and because the outside it needs 8, right? 8 will be a stable state, and then it can attract actually 4 electrons from hydrogen, right? So that's why 4 hydrogen will form a methane with carbon, and both atoms gonna achieve its stable state. So this is how covalent bondings work, right? Instead of giving up and receive, actually both are sharing the electrons. Next one is the metallic bondings. So metallic bonding means they are sharing of the outer shell electrons by all atoms to form a general electron cloud that permeates the entire block. So there's unlike covalent bonding and ionic bonding, so metallic bonding actually forms a cloud of electrons. So all of them are sharing electrons, right? It forms the electron cloud. So in a lot of pure metals, metallic bonding is very, very common. So this is how metallic bonding works. Next, let's look at secondary bonding. So secondary bonding are mostly dealing with the relations of intermolecule, right? Primary bonding are within the molecule, while secondary bonding are dealing with intermolecule forces. And there's no transfer of or sharing of electrons. It's more of something like gravity, right? Something like gravity. And so secondary bondings are a little bit weaker, actually a lot weaker than primary bonds, and there are typically different forms of secondary bonding. The one typical form is hydrogen bonding. So hydrogen bonding means you need to have hydrogen. It's for example the water, right? H2O. It can achieve the hydrogen bonding, and because it's the positive side of hydrogen with another atom's electron, right? So here is positive, while electron has a negative, right? Has a negative charge. So that's why it will start because the two, it's a different charges, so they're gonna attract each other. So this is how we form the hydrogen bonding. Well, another major type of secondary bonding is the van der Waals forces. So for van der Waals forces, it's more of attraction between the molecules, and there are different ways of forming the forces. One is the dipole force. So dipole force means it's between two atoms with equal and opposite electrical charges. For example, this atom, right? It has hydrogen and a chloride. So for hydrogen, it has a positive charge, while chloride has a negative charge. So that's why when the hydrogen is at this side and the chloride at this side, it will form a force because of it has different electrical charges. So form different form dipoles. So that is how they're gonna attract each other. So this is dipole force. Well, London force is a little bit different. London force is formed when because of the electrons are moving really fast, and sometimes a lot of electrons will be at one side, and at the other, and for another atom, the electrons will be at another side. So now you can see most of that electrons are here, while for this atom, most of the electrons are here. So here it will form a attraction between the charges, right? So this is how it forms the London forces. You can take a look at of how these bondings work. So this is a hydrogen bonding between two water molecules, and this is a hydrogen bonding. And let's see how this hydrogen bond, how it works. And for van der Waals forces, you can see those green ones are van der Waals forces. It's a little bit weak, but if it is within the molecule, this is how it formed the molecule. So these bonds are covalent bondings. And they are much stronger than van der Waals bonds or forces. Here is a comparison between different bondings, right? There are ionic bondings, and the covalent bondings are usually very high, high strength, and also have a high melting temperature. Right? Material have high melting temperature, and metallic bondings a little bit weaker than the ionic and covalent bonding. Is because metallic bondings are the cloud, right? So clouds sometimes it can easily lose the electrons. Well, van der Waals forces, because they are secondary bondings, so they are much lower than primary bondings, and weakest is the hydrogen bonding. And also there are some examples, right? Ionic bonding, you can see what it is, what they are. Metallic bonding usually is pure metal, right, with one single element. All right, next, crystalline structures. So crystalline structures are those atoms that they have repeated patterns, right? They have repeated patterns. For example, in the lattice patterns, and it's repeated in a three-dimension space. We can see a lot of materials or actually metals have these crystalline structures. Almost all metals have that crystalline structure. Also, some of the polymers and many ceramics have this crystalline structure as well. Now let's look at different crystalline structures and what are the common metals with what kind of structures. The first type of the crystalline structure is the body-centered cubic. So this is the body-centered cubic. You can see one in the middle, and then all the other are forming around it. So this is how it look like. And also there's a face-centered. So face-centered is a little bit different. You can see there's one atom actually at this surface, right? This is called face-centered. Another one is hexagonal closed pack. So this is how it looks like for hexagonal closed pack structures. And also some examples are shown. You can see for body-centered qubit, because body centered actually can it forms a 3D structure that it's all attract together with very tight packed. That's why for body-centered cubic materials, they are more they usually have high strength. Like chromium, iron, or molybdenum and tungsten, right? If you're familiar with machining, you can see those materials actually are being used a lot in tool materials, right? Cutting tools or some elements that integrated into the tool materials. And also there are face-centered cubic. You can see this aluminum, copper, gold, lead, silver, nickel, and these are the face-centered cubic. Compared to body-centered, they are have lower strength but still have good strength. And and the last one is hexagonal close pack, like magnesium, titanium, and zinc. So for those materials, they have properties that usually they are a little bit light, and also they have very good ductility. Something you need to pay attention to is that so for some of the metals, actually it changes structure at different temperatures. For example, for iron. For iron, at a lower temperature, it's body-centered. When it increases to a certain temperature, it will change to a face-centered. And if you keep increasing the temperature, it will change back to body-centered. And by changing of those structures, people can manipulate the properties of the materials. That's why you probably heard about heat treatment of iron, right? Heat treatment of or steel, and it's so that you can achieve higher either higher strength or stiffness of those materials. All right, next. So not all structures, all crystalline structure are very perfect. So sometimes there are defects. Actually, almost all of them have defects. It's very common. So different defects. So one is a point defect. So point defect means there's a missing of atoms, right? Missing of atoms at a certain point. At a certain point. And certainly the only one atom missing. There are some examples. Like A is one point of the atoms missed, and also B is called iron pair vacancy because it's missing a pair of atoms. And another type is a line defect. So line defect means there are connected group of defects. All the atoms are missing, right? For example. Another type is a surface defect. So surface defect will be a whole surface is distorted, right? Or missing the atoms. For example, the last example like this one, right? So it's more a screw dislocation, right? So those defects usually affects either the surface or the mechanical property of the material as well. Because missing of atoms actually will affect the forming of the structure. If the structure have defects, it will affect the mechanical properties. Deformation of metallic crystals. There are two different kind of strains. One is elastic strain, and another one is a plastic strain. So elastic strain means a structure actually can return back to its original shape. Right? You have extra force or external force applied to it, or stress applied to it, and after you you release the force or release the stress, it actually can return back to its shape, like this one. So it's called elastic strain. Well, another type of strain is you apply a shear stress or force, and then it permanently changed the shape of the material. Right? So it means plastic deformation or plastic strain. You can see this slips plane, so the whole shape has permanently changed. All right. Well, comparing the crystalline structure and non-crystalline structures, you can see crystalline structures are have really regular repeated patterns, while non-crystalline structures does not have that kind of patterns, right? And also non-crystalline structure, because it does not have patterns, so it's a little bit loosely packed. And you can see there are also sometimes there are empty spots or vacancies here and there. So that's why it's a little bit loose. Well, think about the two structures. If it is crystalline structure, usually the material is a little bit heavy, and also it can be more solid, solid material, solid shapes. While it's the non-crystalline structures, usually that's very fluid or gas shaped. So here you can see the two features differentiate non-crystalline structure from crystalline structures. Non-crystalline structures does not have long-range order in molecule structure, and also it has a difference in melting and thermal expansion characteristics. So later we're going to talk about thermal expansion about materials with temperature. And some of the examples of materials with non-crystalline structures are the water, that's a liquid, right, and the air, that's good. Or a metal loses the crystalline structure when melted, right? When you melt the metal, you can see it changes to the liquid shape. And then for that, it loses crystalline structure and it's getting into more of a amorphous structure, which means the atoms are loosely packed. Some engineering materials we use, when they have non-crystalline structure in a solid state, are the glass, rubber, and many plastics. So we're gonna have lectures about the glass and also polymers later in this semester. All right, so for non-crystalline structures, there's volumetric effects comparing the two structures, the crystalline structure and non-crystalline structure. For crystalline structure, you can see the metals. If you keep increasing the temperature, what happens is when it increases to a certain point, right, you usually call it melting point, there is a sudden change of shape. Right? There's a sudden change of shape from crystalline structure, really closely packed, to a loosely packed structure. And this is why the volume of the material actually suddenly increases. So this is a melting point difference. Well, for the glass, it does not have that sudden change. Instead, you can see if you keep melting the glass, it will go through a gradual change instead of sudden change. All right, for metals, now let's look at different engineering materials. For metals, they are almost all the metals have crystalline structures in their solid state, right? Not in their liquid state or other state, but in the solid state, it's almost all crystalline structures. And usually they have body center, face center, hexagonal unit cells, and atoms are held together by metallic bondings, right? Metallic bondings. Typical properties for metals are they have high strength, hardness, high electrical and thermal conductivity. Right, so the reason they can they have good conductivity of electrical is because they form what? They form a cloud, right? Some of them have a metallic bonding. They are cloud of electrons, right? So that's why they can easily have this conductivity feature. And the reason they have high strength and hardness is because what? Because of the structures, right? Because of the structures that closely packed with repeating patterns, not a very loose structure. So for face metals, they are generally very ductile. Next, it's about ceramics. Is another type of the material very common as well. It's an inorganic compound consisting of a metal and one more non-metals, right? One more non-metals. And we'll talk more about ceramics later after we talk about polymers. But now these are just the general properties of ceramics. So most ceramics have a crystalline structure, but there's exceptions. Glass is a amorphous structure, and molecules characterized by ionic or covalent bondings, or both. Right? Typically, ceramics have really high hardness and stiffness, electricity insulating, refractory, and chemically inert. So because of the bondings are really because they have covalent bondings, ionic bondings. So so the bondings are very stable, and the structure is also very stable. That's why it's not conducting electricity very well. The reason they have high hardness and stiffness is also because of the bondings, covalent and ionic bondings have high strength. Well, the polymers, usually we call it plastics, it has many repeating mers in molecule held together by covalent bondings. So a mer is usually a certain pattern, for example, C, H, and maybe something else, right? And then it has repeated patterns of this, and then going to start to create a long chain of the mers. So this is how it creates those polymers. That's why polymers means many mers. So polymers are usually carbon plus one or more other elements, either the hydrogen or nitrogen or some other materials or elements, and they are typically amorphous or mixture of amorphous and crystalline structures. And for the properties, as you can tell, because of the bondings and material structure itself, right? Usually they are low density. Right? Low density because they're amorphous, and a high electrical resistivity is because they do not have very active electrons, right, outside the orbits. So because they have mostly covalent bondings, so this is why they have low conductivity. And also the strengths and the stiffness vary a lot because it really depends on how the mers formed. All right, next let's look at another major topic in this lecture is material mechanical properties. So just now we're talking about different materials and how the material structures are formed. Now let's look at how they're going to affect the mechanical property itself. And what properties are actually critical in manufacturing and in industry. Some of the properties I'm going to talk about include stress-strain relationships, hardness, thermal expansion or effect of temperature on properties, fluid properties, and viscosity, behavior of polymers. All right, first one is the stress-strain relationship. First you need to know there are three types of stresses, right? So So one type of stress is the tensile stress, so which means you are applying forces, right, to the material with two opposite direction of the forces. Well, and typically we stretch it, right? Another type of stress is compressive, means we are having two forces at towards the same point. So this is a compressive stress. You usually call it, squeezing the materials. Another one is shear stress. So shear stress means more like this example. It causes adjacent portion of the material to slide against each other. So there's the three types of stresses on materials. And next, let's look at how do we calculate the stress and strain. So for calculating stress, we use a force, applied force, divided by the cross-sectional area. Right? For example, in the example, we can see the applied force is F, and the cross-sectional area is A. Right? So we just use F divided by A0, so that we get stress. Well, the strain means that it's a ratio that how long it changed by applying the force on the materials. So original length of the specimen or the material is L0 or LO, and you can see the original gauge length, and then amplified the force is stretched, right? It's stretched to L length. So how much it changed is L minus L0, right? And then divided by the original gauge length, L0. So this is how we get a strain. And because the force is different, right? And also if you keep changing the forces over time, when you are stretching something or applying forces, either compression or something else, and so the stress changes and also the strain changes, right? And the strain. So there's a relationship between a stress strain with different materials. For example, if you are stretching say a steel versus stretching a polymer, right? You can see it's different, right? And also the force you need is also different. So that's why it has a stress-strain relationship to characterize different the properties. And for testing, this is a typical setup of the testing. You can watch the video, when you are going through the slides or going through the video, and for the typical setup, it is standardized by the American Society for Testing and Materials for testing the tensile test. So for the tensile test, they apply the forces, pull it up and also pull it down. And you can see we put a test specimen in the middle, and then we're going to measure when the forces apply, and then how the length, right? How the length of the specimen changes until what? Until it breaks, right? Until it fractures. So this is and then we draw a curve to show the stress-strain relationship. So a typical sequence of a tensile test is beginning of test. We have record of the original length and give a preload, right? And then second step is uniform elongation and the reduction of cross-sectional area. So when you're applying the force, you can see the area is actually decreasing, right? It's actually decreasing. So and then the third step is the continual elongation, maximum load reached. So for different materials, there is a maximum load that or force you need to stretch it. Think if you are stretching some kind of soft materials, right? You can handle it, you can break it, right? When you keep applying force, there's a certain amount of time that you need to keep applying force, which is pull it harder, right? Until at a certain point, right, you reach a very maximum force you give, and then you can feel it actually it's not that hard to pull it out, pull it anymore, because it already have this kind of a plastic for deformation, or this neck chips. So that's why you just need to use less force to break it. So that's why there's always a maximum load or maximum force you need for stretching the materials, or give a tensile stress. So later we'll form a neck, you can see, and then it breaks, right? So lastly, you need to measure the final final length of the material. You can calculate, the stress strain and also the Young's modulus. So this is a typical stress strain relationship, and something to notice that there's elastic region and also plastic region. So the elastic region means when you are giving this stress or giving this force, so there's no permanent change, deformation of the material, means it can go back to its original shape. During this period of time, it's called elastic region, right? Elastic region, and after that, there's a point that it will become permanent or deformation. So that strength is called yield strength, right? So it's a turning point from elastic region to a plastic region, or have this permanent deformation. Well, another for the elastic region, it's more linear and or close to linear, while it is plastic region, it's non-linear. And when you keep pulling, right, keep pulling the material, you can see you will reach a maximum load here, and this load is called tensile strength. The maximum load you need for a certain material it's a tensile strength. So here you can see the neck forms, and then later you just need less load in order to break it, until a certain point that the material fractures. Right, so this is a typical stress strain plot, and it is a very important plot, and you need to know how to draw it. You know how to understand the different regions and different turning points, yield strengths and maximum and also tensile strengths. Because for different materials, the plot will be different, and stress strain is a very important property that when you are choosing materials for products, and also design of the products. All right. Next is the Hooke's law. How do we categorize, or how do you measure, right? A material stress strain. If the material have really good stress strain relationship, what does it mean, right? It means if it requires higher strength, right? Or the stress strain has a changing of the curve that really perfectly lines of the manufacturing process, means they have a good modulus elasticity, and it's called Hooke's law to categorize this. Hooke's law means stress equals to E is Young's modulus or modular elasticity. Right? Means how difficult it changes its strain, right? How difficult it changes its strain. So this is Young's modulus. Means if a material have a higher Young's modulus, it means the material actually has higher stiffness, right? Higher stiffness. Equals to stress divided by strain, or Young's modulus equals to stress divided by strain. It's the same equation. And the unit will be MPa, right? So it's the pound divided by square inch. something to pay attention to is the stiffness versus the strength. So stiffness means that how difficult it can change. It can permanently change its shape. For example, the chopsticks, right, versus a rubber band, right? You can keep giving force on chopsticks, and what happens with chopsticks is that at a certain point it will fracture, right? It will break. Well, for a rubber band, you can apply for a really high force, right? Even higher than the than breaking the chopsticks, and still the rubber band can return back to its original shape. So it means what? It means it has high strength. Rubber band has high strength than chopsticks. Well, chopsticks have a higher stiffness than rubber band, right? So the stiffness means how difficult you permanently change its structure or shape. And strength means how difficult it actually fails, the structure fails. And you can see from this table there are different materials and of Young's modulus. And something to notice here is, for example, tungsten. You can see the highest is probably tungsten. It has a 407. Well, compared to some polymers, right? Some polymers, polystyrene or nylon. These have really low stiffness, right? Low stiffness or low Young's modulus. And by using this kind of property, you can actually choose the material for different applications. So sometimes you probably need really high stiffness of materials. Then you can consider tungsten or steel or iron. While if you need some of the lower ones, maybe you can choose polymers. Or if you need extremely high stiffness materials, probably you can use the diamond, right? Or have some trade-offs between stiffness versus strength, and you can probably aluminum or something else. All right, so when we're talking about stress-strain relationships, there's a calculation of ductility. So ductility measure is the elongation. So elongation means, as we just talk about, is equals to the final length, right? Final length minus the original length divided by the original length. Well, some of you probably want to ask the question that because when we are stretching the materials or giving this kind of a tensile load or tensile stress, the area of the material actually changes, right? It's changing. It's not always the same area, right? Because the area is gonna decrease, and how can you use a constant area a constant area value for the prior plot of stress-strain relationship, right? It's the same with the strain, right? Same with the strain, because when the material length changes, right? So the next moments of the length will be different with the prior moment's length. If you are using this original length, right? For example, 1 minute later, the original length will be much probably much higher than the original length of at the 1 minute prior time, So that's why the strength also is cannot be measured always as L0. So L0 is a changing value, and A is also a changing value throughout this kind of a tensile test. So in this case, there are the concept of true stress and true strain. Then you need to use integral function to calculate that. And also we got another curve, which is a two stress strain curve. We still have this elastic region and also plastic region. Just the curve changed a little bit. You can see the necking actually starts from here, and the curve will be a little bit different with the stress, the regional stress strain curve, using the assumed values. Okay, so this is a log scale of a stress strain relationship for material. You can see this, this slope is really long. Well, another type of test is a compression stress test. So compression test is means we are applying forces, right, by squeezing the material. So this compression setup, and when you are squeezing this material, you can see the area is actually increasing compared to a tensile test, right? Tensile test. So this is the compression test. All the other setup are similar. And another type of the stress is the shear stress, and we are testing it. You can see also it's applying forces that two different directions, like this, and you can see this what the curve look like when we are doing the shear stress stress test. This is the plastic region. This is plastic region, and also this is the elastic region. This is the yield point, and also there's fracture here. Next mechanical property is the hardness. So hardness is defined as the resistance to permanent indentation. So hardness is more talking about the surface of the material, right? While the stress strain is more talking about the whole body of the material, right? Whole body material. Hardness is more of a surface material. Means how much resistance it have to the permanent indentation, right? Good hardness generally means the material is resistant to scratching, and wear. And most tools, right, in the manufacturing must have a really good hardness, because once it is scratched, and what happens is that it will cause some defects on the machined surface of the product. In order to test the hardness, there's a hardness test. And really different methods you can use for testing the hardness, but the two common methods are Brinell and also Rockwell. Also, when you are looking at tables about different materials harnesses, they're also in typical scales, like in Brinell method and the Rockwell method. First, Brinell harness test is using a ball indenter. Is using a ball indenter, right? It's ball shaped. So what happens is that the first you're gonna sit the ball on the surface, and then you will give an initial force, right, or initial load, to make sure it penetrates a material at a certain depth, right? And then it will keep giving load, right, increasing the load, and then calculate, right, with the increasing load how much depth it can go, right, how much depth it can go, or how much length, how much di it has, right, how much of the whole ball get into the material. Using this to calculate a calculate a parameter or a value. So this value is a hardness. Now you can tell if it is a low hardness material, it can with the load it can easily get into the surface, right? If it is a really hard material, you probably need a very very high load to get in the material, or you can only get into a little bit depth of the material. So that's this is how you measure the hardness. Well, compared to Brinell hardness test, Rockwell actually uses the cone-shaped, right, indenture. Cone-shaped versus you can see this cone-shaped versus the ball-shaped, right? You can compare the two. Well, for Rockwell hardness test, also there are different scales for measuring different materials. For example, for some softer materials, you can use 100 kg load. Well, if it's a harder material, you probably use 150 kg load. Well, with different loads, right, the values calculated are also different, right? So that's why there are two scales of the values. You can convert them to two. Well, for the Rockwell hardness test, it's pretty much similar to the Brinell hardness test. In principle, first you need to make sure that the indenture is sit on the surface material and give a preload, so make sure it's actually sit on it. And then you will give a major load, either a 100 kg or a 150 kg, and then calculate how much it get into the surface, and then to calculate what is the parameter or the value. You do not need to know what is the equation for calculating the hardness, but you need to understand what is the principle and how those hardness tests actually works. And here is a table about some of the selected materials hardness, and you can see this is Brinell hardness test value. This is Rockwell hardness test value. In the Rockwell, you can also see there's a B scale and also C scales, right? Usually you can actually convert those. Now let's just use one scale. Say we use Rockwell hardness test scale values. You can see there are some really high hardness ones, right? High hardness one will be for example titanium. Titanium is 95B, right? Also the steel have hardness. Also, if steel are differently heat treated or heated for mechanical properties, the hardness is also different, right? Hardness is also different. Actually, the strength is different too. So from the hardness table, you can probably know how to choose different materials for manufacturing applications if you know the working environment of the material for the surface. And effect of temperature on properties. So the temperature has some effect on the mechanical properties of the materials. If the temperature increases, what happens is that usually the tensile strength will and also the yield strength will decrease. And also the hardness will decrease as well, but the elongation or the ductility will increase. And you can see for different material in this graph, for different materials, it changes differently, right? If the hardness changes differently, ceramics it changes really slowly, decreases. But for some other material, for example, high carbon steel, it changes really fast. So using this kind of a graph, we can tell when we are choosing materials for some extreme hot or high temperature environment, right? For example, some oven or some other environments, we probably can consider using ceramic as a surface area, surface of the chamber or some of the materials. So the concept of hot hardness means its ability of a material to retain its hardness at a elevated temperature. So ceramics have higher hardness compared to steel in this case. Last, we're gonna talk about fluid properties. Before just talking about solid materials. Now let's talk about fluid properties. So fluid bodies they take the shape of the container that holds them because fluids they flow. And many manufacturing processes are accomplished on materials converted from solid to liquid by heating. So for example, solidification processes. First, we heat the material into liquid, and then we're gonna inject them into different shapes. For example, your bottled water, right? Bottled water. All these bottles are made of injection molding, right? Injection also for making of different shapes of metals, right? Either a sheet or use some other solid shapes. Then you can use casting processes, right? Casting is also a solidification process, and also it deals with how do you manage the properties of the fluid when they are heated. One important character about the fluid is viscosity. So viscosity is a resistance to flow that is characteristic of a given fluid. How much resistance is to flow. If it's higher viscosity means it's hard to flow. If it's the lower viscosity means it can easily flow, different directions. So viscosity is a measure of internal friction when velocity gradients are present in the fluid. So the more viscous the fluid, the higher the internal friction, right, or the stress it is, and the greater resistance to flow. And so it can be if it is measuring it or when we are defining it, we can look at this graph. So viscosity can be defined using two parallel plates, right, separated by a distance of d, and fluid fills the space between the plates, right. So here it forms a surface, right. Here it forms a surface. And there are two directions, right? One is x, and the other is y direction. Well, we know that for solid materials, there's Young's modulus. We use shear stress divided by shear rate. Well, for a fluid, actually it's similar. When we are measuring viscosity, we also need to use stress divided by strain. So how do we see the stress, right? So shear stress in the fluid is a friction force, right? By the fluid per unit area, right? It's force. So it's just F divided by the plate area A, and shear stress is related to shear rate. So shear rate can be calculated by using the change of velocity divided by change of distance. So V divided by Y. So this is a shear rate. You can see where is the V. V is this direction, right? And also there's the Y. This is a change of distance. So shear rate means it's a velocity gradient perpendicular to the flow direction. So this is the shear rate. and then you can calculate the coefficient of viscosity by using the shear stress divided by shear rate. All right, so for this table, you can see there are different materials viscosity values. There are some high ones, for example, glass, right? Glass has higher viscosity, while the water has really low viscosity, and you can tell from your from your life, right? So this is how you can use the viscosity and to potentially select materials for different applications. Pancake, polymers, mercury, machining oil. And an important application for viscosity is actually in the pipeline. When you are transporting oil, right? A lot of times those kind of oil, crude oil, is actually transported by pipelines, and you need to constantly measure the viscosity of the material, of oil, to make sure you have good quality, not much contamination, and if there's a leak or there are some other changes the pipeline of the environment actually or temperature, right? Viscosity actually gonna change during the transportation. So this is how engineers or managers can manage the transportation by using the value of the viscosity when you're constantly measuring this. All right, so that's all for today's lecture. Mainly I'll talk about the nature of material, different bondings, different crystalline structures. Make sure you understand how the bonding is formed, the primary bondings, secondary bondings, and also what are characteristics of crystalline structures and non-crystalline structures. Next, a major topic is about mechanical properties of materials. We talk about stress strain, right? Talk about hardness. Also understand the difference between stiffness versus strength. And also how the temperature, thermal expansion works. An important part is the stress-strain relationships and also hardness. We're gonna do some labs related to the two as well. All right.